All right. We're in chapter 4. Okay. Newton's laws. We already discussed what they were, right? Inertia. The first law is inertia, right? The second law is F equals m times A. The third law is every force has equal and opposite force, right? So, today, we're going to talk about the free body diagram, right? And the free body diagram allows you to find the resultant force, right? Kind of like what we were doing with the vectors, right? We found a resultant because there were more than one vector applied to an object. So we had to find a resultant. So when something has more than one force on it, right, we have to consider the magnitude of that force and the what? Direction, right? We got to consider the magnitude and direction, and then we have to sum all of the forces together, right? At least those forces which occur along the same plane, right? So the basic example starts with the box, right? Box on a flat surface, okay? Box on a flat surface, right? Okay? So, the question is, what forces are acting on this box? Gravity is one force. And what else? The flat surface going up. So gravity, so think about the free body diagram is that we want to draw our forces and identify in which direction they act. So if we got gravity, then we're going to point down, right? And we're going to call it what? F equals what? M times G. That's the force due to gravity. All right? Which is your weight. So that's the weight of the box. All right? Let's just call it F sub W, right? And right here is F sub W is equal to what? M, which is your mass, times gravity. Where M is mass, G is gravity. Right? Make sure we W. Okay? That's weight. Force of weight. What other force acts on this? Sydney? Yeah, that was Sydney. Sydney said the force from the surface. What do we call that force? Starts with the N. Normal. All right? Remember that from the lecture? Normal force. Remember when we had the statue of Abraham Lincoln sitting on the thing? Y'all don't remember. That was in the lecture. All right? So, normal force. So the normal force, it is in the opposite direction of the weight, right? In order for this to sit at rest on this surface, then the normal force has to do what? Huh? Equal and opposite of the weight. Yes. Okay. But for now, we're just gonna write it there, and we're gonna call it. This is, let's say, this is weight force and normal force. Right? So right now, don't worry about what normal force is equal to. Okay? What other force do we have? Now let's say, okay, well, in order for this box to accelerate in this direction, we have to do what? Apply a force. Let's say we apply the force, and let's say that force was, let's say that force was 50 newtons. Okay? So now we can write F of A is 50 newtons. All right? And let's say the mass of our box is 10 kilos. Okay? So now we got our applied force going this way. All right? So what else? What else is there? Friction, right? Whether it's what? Static. Before it moves, it's static, right? And when it starts moving, it's kinetic. But let's just take static friction first. Okay. Friction. All right, so friction is going to do what? Always oppose what? Huh?
It goes against the force, or the waves
Or goes in the opposite direction of the motion. Right? Better way to look at it, right? The friction is going to be in the opposite direction of the motion of the object. Wherever it's moving, friction is going to work against it. Right? Okay, so now we got four forces. We got we got the weight, the normal, we got an applied force, and let's identify it, right? So we don't forget what A is, what A stands for. This is applied force. So this is what I put on the box to get it to move. That's an applied force. And then we have what? Friction. Excuse me. And the equation for friction force is what? Mu times what? The normal. So what does that tell you? That tells me that what? That my friction force depends on what? Which depends on what? The weight of the box. And that makes sense, right? If the box is heavier, it's gonna have what? More friction. All right? So we got four forces identified. So now we have to do what? We have to sum the forces, right? So first step, we'll say, is that gonna catch my, let me see if my camera gonna catch that.
Yeah. Okay.
Alright, so first step is to do what? Identify what? What did we just do? Identify what? All forces. Right? Magnitude and direction. Now the next step is to do what? Sum all forces in each direction. Sum all forces in each direction. Right? That would be what? X and Y. X and Y. Right? So we remember from our Greek, sigma stands for what? Sum. Right? Sum of the forces in the X. What are the forces in the X direction? According to our figure. The applied force. Right? And so remember, we're gonna always make sure we identify our Cartesian coordinate system, right? So here is what? Positive. Here is what? Negative. At the top is what? Positive. At the bottom is negative. Right? So which direction is my applied force pointing? Positive. So I write it first. Which direction is my friction force pointing? Negative. So I say minus my friction force. Right? And for right now, we don't know if the box is moving or not. But we're gonna assume that it's not. So we're gonna say this equals 0. Alright. Now we're gonna sum our forces in the Y direction. How we do that? What are the forces in the Y direction?
The normal and gravity.
Yes. Which way does the normal point?
Positive.
Positive, so we write that one first. And FW points negative, so we subtract FW, right? And then we subtract FW, right? So is the box moving in the Y direction? No. So this equals what? 0. All right. And I think I left off a couple of things. All right. So let's assume that the static friction is mu of S. Let's write over here now, because this will be our givens over here, right? This will be our givens right here. So let's say where mu of S is equal to 0.4. Okay? So mu is a coefficient, and it's going to be between 0 and 1. It will never be any less than 0 or greater than 1. That's condition. Okay? But for this particular instance, we're going to take it as 0.4. All right? So, because we know that in the Y direction, the box does not move in the Y direction ever. Right? So we can solve for this right here, right? So we can say that f of n So therefore, right, we put the 3 dots like that, that means therefore, right? What? F of n is equal to what? Yes, the weight. Right? Because if I subtract the weight from f of n, I get 0. So they have to be equal to each other. So f of n is equal to what? F of w. And f of w is equal to what? M times g. I said my box was what? 10 kilograms. And my gravity is what? 9.8 meters per second squared. All right, which is gonna give me what? 98 newtons, right? Excuse me. So 98 newtons. So that's what my normal force is, 98 newtons. Or that's what the weight of the box is. 98 newtons, right? So now we're trying to determine what? If I apply 50 newtons of force, will this box move on a surface with a coefficient of friction of 0.4? Right? So how do I do that?
Just put 0.4 times the 98.
Right? So here's f of a. So f of a minus f of fr, right? For the box not to move, then what? This condition must be, well, no. If it doesn't move, then this is true. Right? So what must be true then? They must be equal. So for the box not to move, everybody following what we're doing? The logic we're using? If you don't follow it, say it. It's cool. All right? If you don't follow it, just say, hey, I'm kind of lost here. All right? So in order for the box to move, right? The friction force, right? The applied force has to what? Overcome the friction force. Okay? We know the applied force is 50 newtons, right? So now we need to do what? Calculate the friction force, right? The friction force is what? Friction force is what?
39.2.
All right, 39, right? So friction force would be what? Mu of S times what? F of n. And mu of S is what? 0.4 times what? 98 newtons. So what happened? We got what? 39 what? 0.2 newtons. Right? So, does the applied force exceed the friction force? Yes. So then that means what? It's moving. See, we don't say. I want to make sure we understand this now.
So it's moving that way.
No, the applied force is this way. I applied force this way. The ground put a force back on me that way. But it wasn't enough to stop me. Because I put enough force to overcome it. So now the question is, well, how fast did the box move? How do we do that? Well, since we have recognized that what? The applied force exceeds the friction force, now we know that what? That is moving. So now we're gonna change this to what?
10.8.
Huh?
10.8.
No. What's the sum of the forces equal to?
10.8.
That's a number. I'm asking, what is it equal to? What's the second law? Second law, Newton's second law. The sum of the forces is equal to mass times acceleration. Right? So there's two situations. Kind of like what we did with the projectile motion. Either the box moves or it what? Stays still. If the box stays still, it's equal to, we just did it. Huh? Zero. If the box moves, what is it? Mass times acceleration. It's that simple. But you got to figure out if the applied force is enough to do what? To move the box. Because what if this was what? 30 newtons. What if I applied only 30 newtons? Then what happens? It's not going to move. Nothing's going to happen. You didn't apply enough force to move the box. Okay? So, we back to the question. How do we calculate it? Well, we put mass times acceleration here, right? And then what? Then we just solve for A. So then A will be what? A is equal to what? F applied minus F friction over what? Mass. Did y'all follow me on that? Because I'm getting a couple of confused looks. All right, so this is F applied. This is the friction we just calculated. It's 39. So this would be what? Equals what? 50 newtons minus 39.2 newtons. All of that over what? 10 kilograms. So 50 minus 39.2, what's that gonna give us?
10.8.
Huh?
10.8.
Wait a minute, what? 50 minus 39.2.
10.8.
Oh, 10.8. All right, and then divide that by 10.
1.08.
1.08 meters per second squared. That's how bad. So what is that saying? So we just calculated what? A is equal to 1.08 meters per second squared. So what is that saying? That's saying that what? If I apply, excuse me, if I apply a force of 50 newtons to a box that weighs 10 kilograms on top of a surface with a coefficient of friction of 0.4, then the box is going to accelerate at 1.08 meters per second squared.
How did you get meters per second from Newton and kilograms? Like, how did that just turn into meters per second?
Because a Newton is, what is a Newton? A Newton, forces is Newton, right? Force is Newton. What's the equation for force? Mass times acceleration. So a Newton really is a what? Kilogram per meter per second squared. See that? So if I take the newtons, so this is gonna give me newtons. 50 newtons minus 39.2 newtons, that's gonna give me newtons. So if I take this, put it there instead of this, then that's just gonna leave me with what? Kilograms gonna cancel, and it's gonna leave me with meters per second squared. That's dimensional analysis. That's back from chapter 1. All right? So that's box on a surface, a flat surface. Right? That's the box on the flat surface. So again, if I apply a force of 50 newtons to a box that weighs 10 kilograms on a surface with the coefficient of friction of 0.4, then that box will accelerate at 1.08 meters per second squared. See, it's very important when you calculate problems in physics that after you calculate it, you go back and tell the story to yourself so you can make sense of what you just did. Because a lot of times when we get caught up in calculations, especially with stuff like this, especially if it's your first time, right? It's your first time dealing with free body diagrams, and then it's gonna get more complicated than this because we might have two boxes, all right? We might have one box on the surface, one box hanging from a pulley. That's called an Atwood machine, okay? So, but it's important to, once you arrive at a result, to go back and speak it to yourself and tell yourself, what did I just do? Right? Because then when you start solving, it's gonna make your problem solving process get better over time. Because you're gonna know what you need to do. As soon as you read the problem, you're like, oh, I know exactly what I need to do. Because you said it to yourself so many times. All right? So, yeah, make sure you do that. Whenever you know, especially in these problems, right? Because they got so many steps and you can get lost and forget what you were doing from the very beginning. They need to let me start teaching the second physics because it's a lot of chemistry in the second physics. And well, it's not a lot, but at least you touch on some chemistry. And you know, I'm not quite sure how much they learn in the class now. All right. So. But if I was doing it, yeah, you're gonna learn about some chemistry.
So they won't let you teach it?
I mean, I never, I mean, they assign people every semester, and they never really assign me to the second part of this class. But I can do it. All right, so let's get to the second. Well, it's 12:30. We'll at least start. I guess we'll start. We're not gonna waste that much time. So the second situation, right? We got a box on the incline. I mean, that's the second situation, right? Box on the inclined plane. Okay. So the first one was the box on the flat surface. So now we're on the inclined plane. Why are we on the inclined plane? What did we talk about the inclined plane? What's the point of the inclined plane?
Oh, to make life easier?
Does work for you, right? It's a simple, a simple invention, machine. Simple machines, that's what you learn in physics, right? about simple machines. Simple machines that do work for you. They make your life easier, like an elevator, right? You know, a number of different things, right? Even an airplane is a certain type of simple machine, right? Just the way it's shaped, and the way it cuts through the air, okay? But that's why we're on the inclined plane, because remember what we said about the U-Haul. When you get on the inclined plane, what happens? Huh? Right, so you cut down on which force? Which force you think? Just going back to our the first free body diagram we just did, which force you think that the inclined plane cuts down? Close.
The friction.
Huh?
The friction.
No.
The weight.
The weight. That's the force that gets reduced because of the inclined plane. When you walk up the inclined plane, it's reducing the weight. That's why it's easier for you to go up the inclined plane. Right? And so we're gonna see that, right, mathematically. No, maybe not today, because we might not get that. Right? So, simple machines, right? And that might be a good trivia question, right? Because I like to have those questions too sometimes, right? Good, that's a who wants to be a millionaire type of question. Give me 5 types of simple machines.
Conveyor belts.
What is it?
Like conveyor belts, those things that are like moving.
Escalator.
I don't know about an escalator. Escalator scene. I don't know. I mean, it does. I don't know if it's. I mean, it does move. It does do work technically because it's moving you, right? So yeah, I guess so. What you said?
The conveyor belt, the ones that be in the warehouses.
Oh yeah,
That move the
yeah. I guess those are. I think that's kind of the conveyor belt and escalator. Because that's what I was thinking about, a slingshot. Definitely. Those are combinations of simple machines, right? They take, you know, a really simple machine and another really simple machine and put them together and builds a bigger machine, right?
So like, would a calculator be a simple machine? That's doing like the math for you?
Well, no. What we talking about, when I say work, we talking about like it's moving
Like
something.
physical?
Yeah, physical work.
Okay.
Yeah. Either climbing up some stairs or something like that, or blah, 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 right? See, like with a slingshot, right? It's doing work because all you gotta do is what? Once you pull it, right, you store what? Energy inside the sling.
But then you would be doing work.
The work is coming from when you do what? I mean, when you let it go, that's when it's coming, right? But you stored the energy. You actually did some work, yes, but you didn't throw it though. You see what I'm saying?
So with one of those like baseball machines where you just like put the ball in and it does it with that move?
Like a pitcher.
Yeah.
Yeah, I mean, it probably could be. Yeah. I mean, technically something that like does work, moves something, right? Because what is the equation for work? Force times distance. So if we move something a distance, anything, then that means some work was done. Yeah, some work was involved. Yes, indeed.
Okay, so when you look it up, it says a screw is a simple machine, because that's not the machine in a way.
It's
A drill.
Like a screwdriver, yeah.
Like a
or
drill.
isn't it?
Cause it's like to use screw.
What do you mean?
You just do. Right? I thought a scoop machine was like something like cavemen would use.
Huh?
Like something that uses basic laws of physics.
Yeah, a screw does that.
But
You wouldn't think? A screw?
you just screw
Like,
it in.
huh?
Well, I mean, when you think of a screw as like putting the screw in one spot and then holding a whole construction.
Right. So it's actually it's instead of doing the actual work in terms of moving, it's doing work in terms of what? Not moving. You following me? So if the screw wasn't there, then your thing would do what? Fall apart. Right?
Yeah.
So in order for it to stay together, the screw has to do some work to keep it together. You following what I'm saying? All right. But yeah, that's a good little exercise, right? But yes, but some simple ones, right? Which is the ones I would expect you to talk about, right? And y'all missed the obvious one, right? From the playground. Seesaw, right? The seesaw, and I think they got some other things on the playground that are like simple machines, right?
Wait, so if you say a plane is a simple machine, would that mean like a car is one too?
Well, yeah.
But we also have
I mean, well, I wouldn't call it. I wouldn't. Well, I mean,
Somebody flies
if
a
you say
plane,
yeah,
drive a
yeah.
car.
I mean, and if you say a plane, right? Then I guess we'll just do this next time. So if we, yeah. So if you say a plane, I would put a plane or a car up there with a plane in terms of, I was just, making a real kind of leap, right? Of how a plane cuts through air, and moves objects through air. So yes, a car would be a simple machine. I mean, if you want to call it simple, you know what I'm saying? But I'm thinking, or a car like the Rubbles, right? The Barney car, right? That would be more kind of, that's really what your car is based off of. I mean, technically, you know what I'm saying? You just, huh?
cars where you put your feet. Like a
I mean,
car?
yeah, like a Flintstone car. Technically, it's just that what? You just burn gas. That's why it's so bad for the environment, right? So in order for your car to do work, it has to do what? Burn gas.
So like one of those wheels you put the hamster in.
There you go.
Oh, yeah.
That's a good one.
Yeah.
Do you ever wonder, like, how come things are bad for the earth, but they're already on the earth? Like, whatever's on earth is already there and it's gonna stay there, but how come
True.
things are bad on
But
earth?
see,
Cause you're not supposed to put a fish in the middle of the desert, like certain
Right, I think it's-
certain places.
see, that's the definition. See, what you talking about is technology. Do you know the definition of technology? What technology means? Technology means is the way you do something. That's what a technology is. So even though we got these things on the earth, nothing on the earth is, technically, in my opinion, everything on the earth is supposed to be here. Everything. Now, some things that occur and some things that we have created that were never supposed to be here, like the hydrogen bomb, atom bombs, right? That's one thing. That was never supposed to be here, right? So, but it involves everything that's here on the earth and is gonna always be here. So I really think it's, just the way we have evolved in terms of our technology, the way we've learned how to do things, the way we learn how to communicate with each other, the way we've learned how to transport goods from here to there with airplanes, ships, blah, 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 right? All of those different things, have contributed to, all of the negative impacts. But again, over time, what'll happen, right? And that's what we see happening now, right? That you're starting to see a lot of alternative energy stuff come on board, right? So we start from the Jetsons and we end up where? At not the Jetsons, the Flintstones, and we end up at the Jetsons. With a Tesla, right? So it's just the way whatever technology or the way you doing things at that time, a lot of times that's what's bad, Whatever is here, it was meant to be here, and it's probably supposed to be here, and it's probably, whatever's bad a lot of times is what we created. With what was already here, like you said. Yes, but that's gonna lead to a good discussion in chapter 6 when we talk about energy. Right? Yeah. Because we're gonna do this. We did the box on the flat surface. We're gonna do box on the inclined plane, and we're gonna do the Atwood machine, and we're gonna with 4. We're gonna keep it moving. And like I said, 6 is gonna be more about just what we just did now, about having a conversation about real life type things. Energy is real life, right? When you lose your lights at your house, your life is almost over, right? I know. Y'all can't do nothing without lights and the phone.
Accumulative, like everything?
No, it's just 4 and 6. Last 2 chapters. Oh yeah, we got a test on Friday, right?
Yes.
All right. This Friday. Let's do it this Friday.
And it's 4 and 6?
Huh?
No, it's
No, just 3. Which is vectors and projectile motion. All right. So for that test, like I said, we're gonna review on Wednesday, but we need to understand how to do vectors, right? How to get a resultant vector, right? How to get components, component method, tail to tip method, right? And we need to know, remember the 2 situations we did in projectile motion, where either you start from the ground and you end up back on the ground,
Or you start up and end up
on top of something, or you end up going lower than where you started. Right? In both cases, right? Well, in one case you use the what? In both cases you use the quadratic equation, but with different solutions or different approaches, right? One uses factoring, the other one uses the quadratic equation, or the solution to the quadratic equation.
Like the
Minus B.
B2, 4AC, all of them.
Well, minus B plus or minus the square root of B squared minus 4AC, yeah. All right? So yeah, so on Wednesday we'll review. All right. All right. See you later. Uh-oh. Oh, I had that on.